Hello and welcome to Lesson 5.3 Part 2, where we are continuing our process of completing the square, but we're going to use it to discover the quadratic formula. We're going to derive the quadratic formula in this video, and then we'll do a quick example. So this derivation, I guess you'd call it, you don't have to watch this. I'm not going to really test you on it, but it's pretty neat, and it's something we do in class that I challenge everybody to try for themselves. Before I get started on this, if you'd like, if you're only here to see an example on how to use the quadratic formula, here is example 4. Just scroll ahead until you see that again, okay? If that's you. If not, here we go. So the origin of the quadratic formula actually comes from completing the square. And that's what we're going to do here. So I actually challenge my students in class to try and find this on their own without me. But this is kind of the video if you're absent or if you just want to see it again nice and clean. Here is deriving the quadratic formula. So you can notice here I've got these steps, the general steps for completing the square. This is what you would do regardless of whatever problem you're working on. You'd factor out a, you'd complete the square and keep it balanced. You'd factor, and then you combine like terms. You get the isolated term by itself, and then you take the square root of both sides and you simplify that result. And then solve. I guess that would have been step 7. Hey, let's add that. Can we add that real quick? Step 7. Ooh, not step 70. Step 7. Oh, gosh. Come on. Solve for x. There we go. Okay. All right. There we go. So I'll reference these steps as we move along, but let's go ahead and get started. So I'm going to start with step 1, which is factoring out a if a is not 1. Now, when I'm looking at the general form equation, ax squared plus bx plus c equals 0, well, I don't know whether a is 1 or not. I guess it could be, but it may not be. So to cover our butts, we're going to factor out a. Because, okay, look, if it is 1, then factoring out 1 has no real consequence, right? It's just factoring out 1 and it's not a big deal. But if it's not 1, then we need to do that. Otherwise, completing the square is not going to work. So let's do that. We're going to factor out a, and what is left inside is x squared plus, what goes here? B over a times x. You might be saying, how? Well, if I took a times b over a, the a's would cancel and I'd be left with b again. So that is how I factor out a. Plus c equals 0. Okay. Now we would like to complete the square. All right, so I'm going to do this in blue. To complete the square, we need to add b over 2 squared. If you remember my little jingle from completing square video, it was take the b guy, divide him by 2, then square it. So if we take b, which I want you to notice, b's different now. We're not talking about this b because we factored out a. The b we're talking about is this. It's the coefficient on the x term. So, little star, I am taking b over a, and I am dividing that by 2, and I am squaring that result. Now, b over a over 2 kind of looks like this. It's b over a divided by 2 over 1. Now, you can keep change flip if you know how to divide fractions. 1/2, and then I have b over 2a squared. Or maybe you just know fractions and division really well and didn't need to write all those intermediate steps and can just jump to that conclusion. Of course, let me actually square this thing. It is b squared because b times b And 2a times 2a is 4a squared. So what I'm going to be adding here is b squared over 4a squared. That is what's going to help me complete the square. So I'll say a times x squared plus b over a x plus b squared over 4a squared. And then I must keep it balanced. You see, balance the equation. We must keep it balanced. So here's my plus c. Now what I've added to the equation is a times b squared over 4a squared. So I need to subtract simultaneously this a right here, times b squared over 4a squared. And this equals 0 still. Okay. So now I'm going to, let's do green. And here's my little green dot. I'm going to factor the perfect square trinomial, meaning this guy. That is factorable. Now, we could use a little factoring puzzle. It's a little difficult to think of here. It's b squared over 4a squared and b over a here. But if you've, well, how do I say this? If you've done enough completing the square problems, you know that every time we complete the square on x squared plus bx, it turns into x plus b over 2 squared. Every time. So really, I just need to do b over 2a and cut it in half like that. B over 2a. And if you weren't sure about doing that, I mean, look, b times b is b squared. 2a times 2a is 4a squared, right? I have to do the same number twice so that I get that perfect square. And if you're looking at b over 2a plus b over 2a, b over 2a again, that equals 2b over 2a, which is just b over a, right? So it does indeed work. So this is going to factor like so. A times, this will be x plus b over 2a squared. Then I have my plus c minus, I could do a little bit of work here. I don't have to. Let me look at this. A times b squared over 4a squared. Well, let me ask you, what is a times 1 over a squared? You should say it's a over a squared, which is really just a over a times a, which is just 1 over a. So you see how there's an a on the bottom, right? So when I multiply this a and this 4, right, 4a squared, in the denominator, I should get b squared over 4a. All right? And this equals 0. Okay. Now, step 4 is to combine like terms. Now, how do I say this? You might be saying, when I'm generalizing this process, you might be saying, well, what the heck is a like term now? Well, constants are like terms, right? So, for instance, if I have k plus 2, well, if I say that k is constant, these go together, right? But the minute I say ax plus 2, well, x is a variable. Well, I don't know if this is coming across that well. I'm trying to explain what combined like terms looks like here. You know what it means in the context of constants, right? 7 plus 2 versus 7 plus 2x. This equals 9. This equals 7 plus 2x. So I don't fiddle with that, right? Well, the thing is, this c minus b squared over 4a, those are constants, which means they could be combined potentially. So what I'm going to do here is get a common denominator, because I can combine these things if I do that. If I say C times 4A over 4A, this tells me I've got 4A times C over 4A minus B squared over 4A. Well, that just becomes 4AC minus B squared over 4A. Hooray, look at that. So, now that I have these combined, I can write A times X plus B over 2A squared plus 4AC minus B squared over 4A equals 0. Now we want to isolate the perfect square term. So let's choose yet another color. Let's do purple. Purple. I want to isolate the perfect square term. So to do that, I'm going to subtract this. Subtract this to the other side. This gets me A times X plus B over... I don't really like that. I don't like that I had to write all that. I'm glad I wrote it for you to see here so you see what I'm doing, but I don't want that in the official copy of the notes. Look at this. Subtract that term to the other side. It's negative 4AC minus B squared over 4A. From here, divide both sides by A. And what you should get is X plus B over 2A squared equals... Now I'm going to do a couple things here. I'm going to distribute this negative here and here, just because I want to, no particular reason at all. And this equals B squared minus 4AC over 4A over A is 4A squared. Okay. Now I want to take the square root of both sides. So what's a good color here? What do you like? Do we want to go back to red? How about this like salmon color-ish? How about that? Let's do that. Is that salmon? I don't know. Let's take the square root of both sides and simplify. So if I say square root of X plus B over 2A squared equals... Now when I take a square root, I must account for the positive and negative solution. So I say plus or minus. You could do... Let's see. We'll just put the whole thing under a square root. But I want you to notice that the bottom is a perfect square. Square root of 4A squared. So you can actually simplify this as plus or minus square root B squared minus 4AC divided by 2A. Because the square root of 4 is 2 and the square root of A squared is A. So I get those. All right. Finally, we want to solve for X. So let me switch to maybe this light green. Solve for X. So I've got is X plus B over 2A equals plus or minus square root B squared minus 4AC over 2A. And I'm just going to subtract this. Subtract. This yields X equals B over 2A, negative B over 2A, plus or minus square root b squared minus 4ac over 2a. But notice these have a common denominator. So, to top it all off, here, you know what? I want to move this just a little bit to the right. Here's what I'm going to do. I'm going to take this. I'm going to move it just a little bit to the right. Therefore, x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. And that is the quadratic formula. I want to make that a nice rectangle. Sorry, you know I'm picky about it. Beautiful. Absolutely stunning. Look at that. Look how awesome all that is. Oh, and I guess it's kind of nicely color-coded too, isn't it? I know it's maybe a lot of color, but at least you can associate each step with what's going on. And there you have it. That is the proof. Or I guess it's not so much a proof, but just a derivation. I have derived the quadratic formula from a standard form equation. So notice, completing the square gives you the quadratic formula, meaning they're really not any different from each other. They are the same thing. The quadratic formula is the completed process of completing the square. And there it is. Fantastic. Well, let's go use this now. Let's go use this as an example. Now you might say, so if the quadratic formula just works for everything, why do we really bother learning completing the square? Right? I mean, wouldn't completing the square be an obsolete process if we have a formula that solves each quadratic instantly? I mean, why even factor, right? Why even bother factoring if we have a formula that, given any a, b, c constants, I can solve? Well, answer lies in, one, we value the process more than the result, because that's how what mathematicians do, at least some. And two, maybe more important, well, actually not more importantly, but two, you will use completing the square in other contexts. There are particular calculus problems that require completing the square for success. In fact, completing the square will come around back like a boomerang right towards the end of our year when we start talking about conic sections. And we will need that again because we're going to be looking at parabolas again. And it's very useful for doing that. Okay, so let's just use it. This is just a practice example to see how the quadratic formula is used, okay? So I'm just going to solve for x. X equals, did I sing the song? I don't know if I sang the song. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. It's like Pop Goes the Weasel. That's something to help you remember. But let's actually put this in. So x equals negative b. All right, that's b, that's c, that's a. So that's negative 10 plus or minus the square root of 10 squared minus 4 times a is 2 times c is 11 all over 2 times a is 2. So I say x equals negative 10 plus or minus the square root of 100 minus, 4 times 2 is 8. 8 times 11 is 88. All over 2 times 2, which is 4. So then I will say plus or minus square root of 100 minus 88 is that 12? Okay, all over 4. But of course, square root 12 equals the square root of 4 times 3, which equals the square root of 4 times the square root of 3, which equals 2 root 3. So then this is x equals negative 10 plus or minus 2 root 3 over 4. And now if I divide everything by 2, right, there's a common factor of 2 between the numerator and denominator. Then I say x equals negative 5 plus or minus root 3 over 2. And that is our answer. And that's it. That's the quadratic formula in action. So I want you to notice it's pretty quick, isn't it? Right? You should be able to make these calculations very fast, especially because I let you use a calculator, right? 10 squared minus 4 times 2 times 11, no excuse you can't do that, right? 100 minus 80, done. Like you should be able to do it by hand. You should be able to do it with a calculator. You should be fine, all right? The only tricky thing about using the quadratic formula is making sure you properly simplify your radicals. And maybe if your ABC values start becoming fractions, you'll want to be careful with those. But in general, not a big deal, right? Really rather straightforward, I think, for an advanced Algebra 2 student, that is. If you're watching this video in Algebra 1, this might be new for you, and that's okay. Okay, so that's pretty much it. I do want to show you real quick, though, that this is, in fact, the answer. Let's see, 2, 10, and 11. Let us do that. We'll do 2x squared plus 10x plus 11. Notice my roots are here. So negative 1.634. What did I say? Negative 5 plus root 3 over 2. So if I say negative 5 plus square root 3 over 2, those values match, right? Those are the same values. And the other answer is changing that plus to a minus, which incidentally is that point 2. Okay? And there you go. That is the quadratic formula in action, but it's really not, it's not that taxing, right? And there you go. Oh my gosh. This is just so wonderful. What a wonderful lesson. I hope you've enjoyed watching this. I hope this was a fun little exploration on deriving the quadratic formula, and I'll see you around.